Bismillahirrahmanirrahim. Welcome to Physics second year lesson. In the previous lesson, we discussed about mass effect and binding energy. Then we discussed about the interaction of radiation with matters. In this lesson, we will discuss about the last two topics of the reduced syllabus, that is basic forces of nature and building blocks of matter. First of all, we discussed about the basic forces of nature. All the matter in the are all the particle in nature are subjected to some forces. That is, there are four fundamental forces which are the basic interaction between the particles. These four basic forces of nature are strong nuclear force, electromagnetic force, weak nuclear force, and gravitational force. First of all, we discuss about the strong nuclear force or strong force. It is the strongest of all the forces, but it is a very short range force, and it is the force which is responsible for the binding of neutrons and protons within the nuclei. This force actually represents the glue or the attraction that holds the neutron together or protons together, and it is the strongest of all the fundamental forces. But it is a very short range force, that is, it is operative within a distance of 10 raised to power minus 14 meter, which is the size of nucleus. The second force is the electromagnetic force, which is a combination of two forces, that is electric force and magnetic force, but they are combined and named as electromagnetic forces because both the forces are related to the charged particle. When the charge is at rest, it develops only the electric force, but when the charged particle is in motion, then it also develops along with the electric force as the magnetic force. So they are combinedly named as electromagnetic force. And it is 10 raised to power minus 2 times the strength of the strong force. So it is less stronger as compared to the strong nuclear force. And it is the force which is responsible for the binding of atoms and molecules. So in case of atoms, the electron and nucleus, they are binded together to form the atom, whereas in molecules, the molecular attraction or atomic attraction between the two molecules that is being responsible due to the electromagnetic forces. But it is the long range force as compared to the strong force, and it obeys the inverse square law that its strength decreases with the square of the separation between the interacting particles. Then the third force is the weak nuclear force. Weak nuclear force, it is the also the short range force or nuclear force that is responsible for producing the instability in a certain nuclei, and it is the force which is responsible for the most of the radioactive decay processes such as the beta decay, and its strength is only about 10 raised to the power minus 9 times that of the strong nuclear force. So it is also less than the strong nuclear force. And now the scientists believe that the weak and electromagnetic forces are the two manifestations of a single force, and they are named as electroweak force. So the electromagnetic force and the weak nuclear force were combined to give this common name that is named as electroweak force. That was done by Dr. Abdul Salam from Pakistan, Glasgow, and other scientists. Their work was acknowledged by the Nobel Prize. Then the last force, that is the fourth force, that is the gravitational force. It is the longest range force, and its strength is the least. And it is only about 10 raised to the power minus 38 times that of the strong nuclear force. And it is the familiar interaction or the force that holds the planets, plants, stars, and galaxies together its effect on elementary particle is negligible because this force is directly proportional to the product of their masses. So if the mass is large, this force is large, and it also obeys the inverse scale law that its magnitude decreases with the scale of the distance between the two masses. So the gravitational force is the weakest of all the fundamental forces. So these are the four basic forces of nature by which all the particles interact with each other. In modern physics, one often describes the interaction between the particle in terms of exchange of field particles or quantas. So in modern physics, if two particles are attracting or repelling each other, that is due to the interaction of the field particles or energy particles which they exchange with each other. So it means that all the particles are producing or exchanging the energy particle or field particle with each other, and due to their interaction they develop a force. In case of electromagnetic force, the field particles are called photons. So it means that if the two charged particles attract or repel each other, that is due to the interaction or the exchange of the photons. And one can say that the electromagnetic force is mediated by photons. So they exchange the photons, due to which the force develops. Likewise, the strong force is mediated by the field particles which are named as gluons. Similarly, the weak nuclear force is mediated by the particles named as W and Z bosons, and the gravitational force is mediated by the particle named as gravitons. The building blocks of matter. Next topic is the building blocks of matter. It was initially understood that all the matter are composed of atom, and atom is the fundamental particle which cannot be further divided. But with the advancement of science, it was proved that the atom is not a fundamental particle. It is made up of other particles which are named as the electron, protons, and neutrons. And in the last 2 decades, the physicists have made tremendous advancement in our knowledge for the structure of matter by recognizing that all the particles, with the exception of electrons, photons, and then few related particles, are made up of smaller particles which are named as quarks. So thus the proton and neutron, for example, are not truly the elementary particles but are the system of tightly bound quarks. So uh, according to the new theories, the electrons and photons and few other particles, these are the elementary particles or fundamental particles which cannot be further divided, and the other particles are like protons and neutrons. They are not fundamental particles, they are also made up of small particles which are named as quarks. Classification of particles. There is mainly two classifications of particles. That is, first one is hadrons and second one is leptons. First of all, hadrons. Hadrons are the particles which interact through strong nuclear force. These particles are not known as hadrons, and there is further two classifications of hadrons, that is mesons and baryons. Mesons are the particles whose mass is in between the mass of proton and electron. So it means that their mass is less than the mass of proton. And all the mesons are known to decay finally into electrons, positrons, neutrinos, and photons. And the pion is the lightest of known mesons. Then the second classification of hadron particles is the baryons. Baryons are the particles whose mass is either equal or greater than the proton's mass, and protons and neutrons are included in baryons family, as are many other particles with the exception of proton. All the baryons decay in such a way that the end product is including a proton. So in simple way, we can also say that mesons are the particles whose mass is less than the mass of proton, and baryons, their mass is greater or equal to the mass of proton. And the second classification of particle is the leptons. Leptons are the group of particles that participate in weak interaction, and including this are the electron, mesons, and muons and neutrinos, which are all less massive than the lightest hadrons. Since lepton has no internal structure, so they appear to be truly elementary particle, and scientists believe that there are only six leptons: electrons, muons, neutrinos, and their anti-particles, uh, particles such as antineutrino, antimuon, and positron. So it means that leptons are the elementary particle. They are not made up of any other particle, whereas the hadrons are not the elementary particles. They are made up of quarks. So what are the quarks? According to quarks theory, which was initiated by M. Kellerman and G. Zwing, the quarks are proposed as the basic building block of the mesons and baryons. The quark model is based on the following assumption. First one, there are six types of quarks. Their name is up, down, strange, charm, and bottom quark, bottom and top quark, and their symbols are U, D, S, C, B, and P. And for every type of a quark, there is a corresponding anti-quark. So in case of quarks, the quarks combine in three to form the particles like protons and neutrons. So it means that the baryons are composed of three uh, quarks or antiquarks. So antiquarks also combine in three to form antiparticles like antiproton and antineutron. Whereas a meson consists of the quark and antiquark. Or in simple way, we can say that the baryons are the particles which are composed of three quarks or antiquarks, whereas the mesons are the particles which are composed of a quark and antiquark or two quarks. And in terms of charge of electron, these quarks have fractional charge, that is up, charm, and top quarks each carry a charge of plus 2 by 3 e, and the other three quarks, they carry a charge of minus 1 by 3 e. And the antiquark carries an equal but opposite charge to that of the corresponding quark, and the symbol of the antiquark, that is just represented by placing a bar on the symbol, just like this. For example, D bar, this represents the symbol for down antiquark. As we discussed previously, that the baryons are composed of three quarks or antiquarks. So in case of proton, proton is also composed of two up quarks and one down quark. If we see their charge, the up quark contains the charge plus 2 by 3 e, so it's a net charge plus 2 by 3 plus 2 by 3 e, whereas the down quark carries a charge of minus 1 by 3 e, so net charge on the proton is plus 1. Whereas on the neutron, which is consisting of an up quark and two down quarks, so minus 1 by 3 is e is the charge on the down quark, so there will be minus 1 by 3 minus 1 by 3 plus the charge on the up quark plus 2 by 3, we get the 0. So the neutron is the neutral particle. Now we can also understand this phenomenon by this video.
What are quarks? Over the past century, discoveries in physics have come thick and fast. Some have changed the way that we understand the world. An understanding of the structure of the atom has been a huge focus of scientific research, and it has heralded an era of discovery unlike any we have ever seen before. In 1964, Murray Gell-Mann and George Zweig suggested that most of the known particles of the time could be explained as being combinations of three fundamental particles. Now, the term fundamental means that the particle does not have a substructure. It cannot be split. The name quarks was chosen from the James Joyce novel Finnegan's Wake. 3 quarks for Muster Mark. In order for their calculations to work, however, these quarks needed to have a fractional charge. This was a new concept, as fractional charges had never been seen before. Quarks are the fundamental building blocks of all particles that we know of. At the Stanford Linear Accelerator, electrons were fired at protons and found to bounce off of tiny particles inside them. It had taken 4 years, but this was the first evidence for the existence of quarks. At the time, there were 2 basic quarks. The up quark, which has a charge of plus 2/3 of the charge of an electron, and the down quark, which has a charge of minus 1/3. How are they different? They all have different masses, as well as charge, and another property called spin. The up and the down quarks are the most common and least massive. The proton was found to be made of 2 up quarks and 1 down quark. Now, we know that the charge of a proton is +1. If we look at this in terms of the fractional charges given to quarks, 1 up quark would have a charge of +2/3, so therefore 2 up quarks would have an overall charge of +4/3. Adding in a down quark reduces the overall charge to 3/3, which is the equivalent of 1. A neutron was found to consist of 2 down quarks and 1 up quark, which gave it an overall charge of 0. The discovery of the up and the down quark was followed in the coming years by the strange quark, the charm quark, the top quark, and the bottom quark. Quarks have quite strange names. Up and down were named based on components of their spin. Strange quarks were given the name strange because they were observed in particle decays that had slightly longer lifetimes than they should have done. The charmed quark was given the name because of its fascination, the way that it fascinated the physicists at the time. Bottom and top quarks were chosen by a famous physicist called Harari. He chose the names because they were the logical counterparts of the up and down quark. Quarks are never seen on their own, and the evidence for their existence comes only from particle accelerators.
So this was the today's lesson, and now we discuss the exercise of the chapter. First MCQ is the binding energy of a nucleus is 7.7 mega electron volt, and that of a nucleus B is 7.8 MeV. Which nucleus has the larger mass? As we have the relation for binding energy is equal to delta mc square, so the nucleus that is having greater mass will be having greater binding energy. So nucleus B is the correct answer. Then second is how many neutrons are there in the nuclide Zn66. So we can find out the number of neutrons by subtracting the mass number from its atomic number. So subtracting 66 from 30, 30 is the atomic number or proton number of the zinc, so we get 36. The max is equivalent to 931 MeV energy is, as we have to find out the mass, so that is can be found by the relation E is equal to mc square or m is equal to E divided by c square. But first of all, we have to convert this energy into joules. So 931 mega electron volt can be converted into joules by multiplying with 1.6 into 10 raised to power minus 6. So we get the energy in joules, and then we divide with c square, that is c equals to 3 into 10 raised to power 8 meter per second. So we get the answer. Then next is the energy equivalent to the 1 kg of matter